All right, so picking up from last time, I wanted to discuss our Pauli exclusion principle. We've alluded to this in prior lectures, but let's just make sure that we say this outright. No two localized electrons can simultaneously have the same quantum state. In other words, they can't have the same quantum numbers. And when I say localized, I mean um, uh, within a small vicinity. So so what this means is as you start putting uh, electrons into an atom, um, the the quantum numbers uh, once used can't be repeated. So not all of the electrons can drop into the ground state, which um, which you might think that out of necessity they would all go to the lowest energy, which is the ground state. Instead, they go in our simple assumption to the lowest energy state available. And so once the ground state energy is full, they have to go to the next set up. So here, um, remember from our Schrodinger equation solved for the atom, we had three quantum numbers, and then experiment and practice showed us that there is this fourth quantum number. Um, so let's put all of this together. And uh, so if n is 1, then L must be 0. And if L is 0, M sub L must be 0. Um, and the same limit uh, falls for M sub S, that it can either be spin up or spin down. And so uh, for n equals 1, there are two possible electron configurations: 1, 0, 0 spin up and 1, 0, 0 spin. For n equals 2, stuff starts to get a little more interesting, right? Because you could have n is 2, L is 0, M sub L is 0, and again, M sub S could either be spin up or spin down. So you could have 2, 0, 0 spin up and 2, 0, 0 spin down. But you could also have n is equal to 2 and L is equal to 1. And here's where things start to get interesting, right? Because if L is equal to 1, then M sub L can take on any value -1, 0, or +1. In this case, not only do you have the two 0, 0 spin up and spin down cases, you have the 2, 1, -1 spin up, spin down, you have the 2, 1, 0 spin up, spin down, and you have the 2, 1, 1 spin up, spin down, for a total of 2, 4, 6, 8 possible uh, distinct set of quantum numbers. For the n equals 3 case, and you'll note that we stopped with n equals 3 because um, if we go to n equals 4, I would have to make this box smaller, and once I got this far, I was too lazy uh, to start over again so that I could fit the n equals 4 case here. But again, you could have 3, 0, 0 spin up and 3, 0, 0 spin down. You could have 3, 1, -1 spin up, 3, 1, -1 spin down. You could have 3, 1, 0 spin up. You could have 3, 1, 0 spin down. You could have 3, 1, 1 spin up. You could have 3, 1, 1 spin down. Additionally, you could have 3, 2. Oh, goodness. Um, hold on one second. All right. Not my finest moment, but um, you could also have 3, 2, -2 spin up. You could have 3, 2, -2 spin down. You could have 3, 2, minus 1 spin up. You could have 3, 2, minus 1 spin down. You could have 3, 2, 0 spin up. You could have 3, 2, 0 spin down. You could have 3, 2, 1 spin up. You could have 3, 2, 1 spin down. You could have 3, 2, 2 spin up. Or you could have 3, 2, 2 spin down for a total of 2, 4, 6, 8, 10, 12, 14, 16, 18 possible cases. So this gives us that the possible number of states goes as 2n squared, right? When n was 1, 1 squared is 1 times 2 is 2, and we had 2 states. When n is 2, 2 squared is 4 times 2 is 8. And note that we had 2, 4, 6, 8 possible states. When n is 3, 3 squared, 9 times 2 is 18, and we had 2, 4, 6, 8, 10, 12, 14, 16, 18 possible states. Hopefully that's okay. So hopefully you can figure out how many possible states we would have for the n equals 4 case, right? 4 squared, 16 times 2, 32. Hooray. Okay, so let's look at Hund's rule. And you might have seen this in your chemistry class before. When an atom has orbitals of equal energy, the order in which you fill is such that the maximum number of electrons have unpaired spins. And when I say unpaired spins, I mean um, a spin up without a spin down, or a spin down without a spin up. So, um, so for the n equals 2 case, right, as you're adding the n equals 2 electrons, um, or let's go to n equals 3. Um, the the first thing that you're going to do is you're going to try and put electrons in without going spin up and spin down. And so let's follow through here. So if you take out your handy dandy periodic table and start with the atom lithium, you have 3 electrons to count for. So the first 2 electrons are going to go into the lowest state, 1s. The next electron you add is going to go in as either spin up or spin down, right? For beryllium, 4 electrons to account for, you're going to have the 1s filled and the 2s filled. For boron, 5 electrons to account for, the 1s and the 2s are both full, and you're going to add an electron to the 2p. For carbon, here's where we start to see Hund's rule in effect. For carbon, again, the 1s and the 2s are full. Rather than going spin up and spin down in this first 2p state, instead you're going to say the 1s, the 2s are both full, and then you're going to put 2 electrons into your 6 available 2p states, but you're going to not put them into the same bin so that you have to go spin up and spin down. Instead, so coming back to this, right? Instead, you're going to first put a spin up in one of these bins, and then you're going to put a spin up in the next bin. Again, our goal is to maximize the number of unpaired spins. When we go to nitrogen with our 7th electron, again, we're going to first fill up the 1s and 2s, and then when we get to the 2p, we're going to put a spin up into each of the 2p bins. And then when we get to oxygen, with 8 electrons to account for, we, again, fill the 1s and the 2s. Sorry for jumping back and forth. First, we're going to fill the 1s and the 2s. And then we're going to put 1 into each of the 3 bins for 2p. And then we still have 1 more electron to account for. And now we have no choice. We have to put this one in spin down. And then for F, adding yet 1 more electron. Again, now we have 2 bins in this 2p state that have both a spin up and a spin down. And then by the time we get to neon, the 1s is full, the 2s is full, and the 2p is full. Yay? So hopefully this Hund's rule makes sense given kind of this filling chart. Now, before I scroll down further, bear in mind that all the chart that I'm about to show you is trying to illustrate is this idea of selection rules. When an electron transitions from one state to another, the selection rules are such that delta L is plus or minus 1, delta M sub L is either 0 or plus or minus 1, and delta MS is going to be 0. And so with that said, and with apologies, we have the following. So I guess it would be nice if we could see all of this at once. So maybe I will bring these here just so that we can remember. And so on the left, I've plotted the n values, and notice on the right, I've plotted energies of these n values. And so, so note that they start out spaced far apart, and as they get to greater and greater n's, these levels get closer and closer together, right? But these represent the allowed L values, right? And so, and the L values correspond to S, P, D, F, and G. Perhaps later we'll talk about where these come from. It's kind of an anachronism, to be honest, but the n equals 1 case, remember from way up here, insists that L go to 0, right? And so there's only one little ledge here for the n equals 1 case that also corresponds to L equals 0, right? So if I put yay, the n equals 2 case, again, coming up to our little chart, n equals 2 allowed L to be either 0 or 1. And so notice that there are 2 ledges here for n equals 2, one corresponding to L equals 0 and one corresponding to L equals 1. Hooray. For n equals 3, there's 3 ledges, one associated with L is 0, one associated with P is 1. Sorry. Wow, bad mark. One associated with L is 0, one associated with L is 1, and one associated with L is 2. For 4, there are 4 ledges for L equals 0, L equals 1, L equals 2, L equals 3. And by the time you get up to sorry, I should pause the video, but instead I'm just going to keep going. By the time you get up to these very, very high n values, there are also a very, very high number of little ledges, right? But the rules still stand that the allowed transitions allow for delta L to go as plus or minus 1. And so from the n equals 1 case, you can jump only to the L equals, so for n equals 1, L is 0. The only way that you can get a delta L of plus or minus 1 is jumping from anything in this L equals 1 column, right? And so I will zoom in a little, right? So you have these allowed transitions from this column of ledges down to here. When you get up to n equals 2, now things start to get confusing, right? Especially if you have a color vision deficit like I do. And so I tried to maintain a color coding here, and I've been told that I failed. But for the n equals 2, L equals 0 ledge, again, you can only jump from, you can only jump, has to be one of the elevated ones, right? You can only jump from the L equals 1, right? So you can jump from down here to up here, or you can jump from up here to down here, right? You can't jump from here to here, right? You can't jump straight down because that wouldn't be a delta L as plus or minus 1. But if you have n equals 2 and L equals 1 from this ledge, now you can either go to the L equals 0 ledges, or you can go to the L equals 2 ledges. Yay? When you get up to n equals 3, again, stuff gets crazier the higher up here you go. If you're in the n equals 3, L equals 0 case, well, again, you have to jump to one of the ones in the L equals 1 column of ledges. But if you're in this n equals 3, L equals 1, you can jump to the ledges allowed by the L equals 0, or you can jump to the allowed ledges for L equals 2. If you're in the n equals 3, L equals 2 case, well, then you can jump to the columns for L equals 1 or the columns for L equals 3, and so on and so forth. Hopefully that is okay. Note that we haven't even added in the m sub l's, just because that would make this graph far, far too cluttered. So I'll leave it here for a moment so that you can at least try and gauge what's going on from n equals 1 to n equals 4. Maybe pause the video. I'm going to scroll on. Okay, so we're going to say that a photon has a maximum angular momentum of 1 h bar on any of its axes, and the photon energy hf is also hc over lambda, is just going to go as ei minus ef, and here we've again plotted our energies. Remember that this is for the hydrogen atom, right? So those energies aren't for every atom. Okay, so now let's start looking at more complicated atoms. And so let's look at the ground state of an atom that has Z protons. And so this time, psi 100 n, l, and m sub l is going to go as some coefficient C100 times e to the minus zr over a naught, where a naught is still 0.0529 nanometers. Notice that this looks very familiar to our hydrogen atom, right? And it should, because you could set z equal to 1. We still need to be able to normalize this, so it still needs to be such that the integral of psi squared psi dv is equal to 1, and we still have that dv follows this statement from our last lecture. Um, we have that 0 is less than phi is less than 2 pi, 0 is less than theta is less than pi, 0 is less than r is less than infinity. And so you can, I hesitate to say simplify, but you can simplify this integral as such. Last time, remember, we were looking at separable solutions, and so let's take this triple integral and notice that this stuff doesn't have phi in it directly, and so bring the phi out front. Integral 0 to 2 pi of d phi is just going to add a 2 pi. Sine theta d theta integrated integrated from 0 to pi, and then multiplied by 0 to infinity, psi star psi r squared dr. And what you get, subbing in our ground state psi11 for psi, and then psi star psi is just the square of that in this case. So instead of e to the minus zr over a naught, squaring it, it's e to the minus 2 zr over a naught, right? And then again times the coefficient C100 squared. By the magic of Mathematica, I am going to tell you that you could also use a table of integrals for this. That all of this winds up being 4 pi times C100 squared times a naught cubed over 4z cubed. If you just wanted to look at this last little bit of integral, we did it here for you. Again, this term is just 2 pi, and this term is just 2. And so 4 pi times this coefficient squared times this integral, which just adds our a naught cubed over 4z cubed, right? By normalization, we integrated this over all space, and so it had to equal 1. We can use that to solve for what we mean by C100. And it is 1 over pi times z over a naught to the 3 halves, yielding the normalized wave function in the ground state as 1 over square root pi quantity z over a naught end quantity to the 3 halves times e to the minus zr over a naught. And what this looks like is kind of like a sponge that has been cut into a spherical shape. And you might imagine that it's densest in the middle and it gets less dense as you go outwards. That's kind of what I was trying to draw here. I think I tried to show it being higher probability density in the middle and getting less dense as you go outwards. I'm not sure how well I've drawn that, but forgive me, it's about to get worse. The n equals 2 case, this is our first excited state, right? So we have the psi 200 case. The solutions look like this: C200 times quantity 2 minus zr over a naught end quantity times e to the minus zr over 2 a naught. if you normalize this, you're going to get uh, a blob in the middle that is fairly dense, and then kind of a spherical shell, a diffuse spherical shell around that. 210, psi 210, again, some coefficient multiplied by z, r over a naught, times e to the minus z, r over 2a naught, all of that times cosine theta. This sort of looks like a pair of spheres, one above the other, separated by some amount, but the the bottom portion of the top sphere and the upper part of the lower sphere are the most dense, and it gets kind of diffuse, sparse as you go to the spherical shell, um, on either the upper part of the upper sphere or the lower part of the lower sphere. Here, I would definitely recommend Google. Google is your friend for seeing a figure of what this really should look like. Psi of 2, 1 plus 1 and psi of 2, 1 minus 1 look like some coefficient C211 times z r over a naught e to the minus z r over 2 a naught times this time sine of theta, and this time also times e to the plus I phi if you're talking about the plus 1 case, and it's all of that times e to the minus I phi for the minus 1 case, right? So remember, n, l, and m sub l. N is 2, l is 1, m sub l is either plus 1 or m sub l is minus 1. In this case, if you try and plot this, again you have uh, some spherical blobs, again with more density. This one you can think of as side to side. You can think of this as having, again, more density on the inner part of the sphere than the outer part of the sphere. Again, Google to see what these actually look like, and then try and draw it yourself before you judge me for my poor artwork, or don't. It's fine. I know I'm a bad artist, a poor artist. Um, let's look at the total angular momentum. So the total angular momentum is going to be the orbital angular momentum plus the spin angular momentum. That even makes sense classically. And um, classically, J should be able to take the total angular momentum, should be able to take on any value in between uh, uh, the the ranges of uh, minus quantity L plus S and plus L plus S. In quantum mechanics, that's actually not so. Um, in quantum mechanics, like everything else, this is a quantized, uh, like everything else we've looked at, this is quantized. And we can say that the total angular momentum is going to take on some value of h bar times the square root of j times quantity j plus 1 and quantity. And what do we mean by allowed values of lowercase j? Well, if L is not equal to 0, then it's just equal to L plus half and L minus half. If L is equal to 0, it's just equal to half. And so let's look at a case where we can kind of explore this. So if L is 1 and S is half, well, then we can say uh, L is not 0, so we'd be looking at this case, right? And so J should take on the value of L plus half or L minus half. Here I've drawn the J is 3/2 version. That's where L plus S is the version, right? So L plus S gives J, and it's going to take on the value of I that you get if you plug in little j is equal to 3/2 here. Hooray! So 3 halves plus 1 is 5 halves times 3 halves is 15 fourths. So square root of 15 fourths times h bar. Hopefully I didn't screw that up. Um, basic math always gets. The other option, because L isn't 0 here, L is 1, is that little j takes on the value of L minus half. And so if L is 1, L minus half is half. And so little j takes on the value of half. Half plus 1 is 3 halves times half is 3 fourths. So square root of that is square root 3 over 2, square root of 3 fourths, or square root of 3 in quantity divided by 2 times h bar, right? In this case, L minus S yields J, right? So hopefully that's all right. Hopefully we're okay with that. I wanted to briefly talk about the spin orbit effect. And so this is an interesting curiosity of experiment that if you have atomic states that have the same value of n and L, but they have different J values, they also will have slightly different energies, and this is because of the electron spin interacting with its orbital motion. This is sometimes often referred to as fine structure splitting. And so if we think about this from kind of one perspective, you have this proton and the electron orbiting, so I guess this would be our hydrogen atom. But just imagine some nucleus with some number of protons and the electron orbiting. But you could also jump into the reference frame of the electron, where the electron is sitting still and it sees the proton orbiting us. You might harken back to kind of the ancient debate about whether we had a heliocentric or a geocentric universe, right? In fact, the universe is neither heliocentric nor geocentric, but our solar system is heliocentric, right? Sun-centered. It kind of took a little bit to suss out the answer to that, though, because a lot of the observations that you could make with just the naked eye, you could argue for a sun-centered or an Earth-centered solar system or a universe if you only have kind of restricted data, right? Well, here a lot, in this two-body system could be explained from either vantage point. And so let's jump onto the electron's frame of reference where the proton orbits it. Then from physics 230, you probably remember that that you could think of this proton orbiting this electron as kind of a modified current loop that is going to produce a magnetic field upwards inside the loop. Hopefully that's all right. I'm going to move it outside the loop. Forgive me. As far as the electron's concerned, there's this this magnetic field pointing upwards. And now that takes this 2p energy level, right? N and L. So in this case, let's let it be N is 2 and in L is 1. And note that this can actually split the 2p state into two energy levels that are slightly distinct. And one of them corresponds to the magnetic field and L and S pointing in the same direction, and the the moment pointing in the opposite direction. And the lower of these two energies corresponds to the magnetic field L and the moment pointing in the same direction, and S pointing in the opposite direction. And so they're going to differ by an amount delta U, and delta U is just going to equal 2 times the moment times the magnetic field. If this part doesn't make sense, that's all right. I am not going to really hold you accountable for fine structure splitting. So I will come back and talk about shell symbols, since you are likely to see this in a chemistry course. N equals 1 is capital K, N equals 2 is capital L, N equals 3 is capital M, 4 is capital N, 5 is capital O, 6 is capital P, and so on and so forth, increasing the alphabet. For L, our subshells, L is 0 gets S, L is 1 gets P, L is 2 gets D, L is 3 is F, and now it goes alphabetically. 4 is G, 5 is H. So let's go through our periodic table, at least part ways, so that you can start to get the gist of what's going on here. For helium, Z is 2, and so there's 2 electrons that we're going to have to account for, and in the ground state, it's going to go as 1s2. So N is 1, L is 0, and we're going to put 2 electrons in there. So the ground state, we're talking about the K shell, right? N is 1, L is 0, M sub L is 0, and M sub S is either spin up or spin down. M sub S is either plus or minus half. Yay? By the way, the notation I use for spin up is an up arrow. The notation I use for spin down is a down arrow, but what I really mean is M sub S is either plus half or M sub S is minus half. I realized that I used that shorthand earlier and hadn't yet, at least in this lecture, described it. I don't know if I did in the last lecture. This corresponds to S is equal to 0 and L is equal to 0. Why is S equal to 0? Because since in the ground state 1s2, one has to go spin up, one has to go spin down, and so the two are going to wind up canceling each other for a total spin of 0 spin angular momentum. Since L is 0, we also have that capital L is 0, right? And since J is just S plus L, if these are both 0, then J is 0 also. The thing that I'll note here is that the ionization energy is 24.6 electron volts. This is big. This is a big value. Because the ionization energy is 24.6 electron volts, because this is a large value, it makes helium rather inert, right? This is why it's a noble gas. It doesn't, it's very hard to get enough energy to liberate these electrons, and so it doesn't interact well. It's unlikely to want to bond with anything, because you would need to mess with the electron before that could happen, and it costs a lot of energy to do that. For lithium, Z is 3. And so we have uh, in the ground state 1s2, 2s1. The K shell is filled, and one of these electrons has to go into the L shell. The uh, the energy winds up looking like minus half K Z prime E squared over R. Um, in this case, the ionization energy is 5.39 electron volts. Notice this is much smaller than this. Because the ionization energy is so small, uh, it is actually very active. It's very willing uh, uh, to interact with other atoms and uh, and uh, allow this electron to be part of other bondings. So in this case, so since we gave you that this is 5.39, let's look at a quick example. So if the third electron in lithium were at the n equals 2 state according to Bohr, um, you'd have Z prime E is 1e, would give a binding energy of minus 13.6 electron volts over 2 squared is minus 3.4 electron volts. But instead, the binding energy is 5.39 electron volts. And so let's figure out what Z prime is. So um, if n is equal to 2, then R is equal to 4a naught. Hopefully that makes sense after prior lectures. So we could say that E naught is just K E squared over 2a naught is 13.6 electron volts. Instead, what we're seeing is E is half K Z prime E squared over R. And so we can plug in 5.39 electron volts into this. Minus 5.39 electron volts is equal to minus half K Z prime E squared over 4a naught. So plug in our value of R as 4a naught. This simplifies to minus Z prime over 4 times K E squared over 2a naught. But we already know that K E squared over 2a naught is 13.6 electron volts. And so this is just minus Z prime over 4 times 13.6 electron volts. So in order for that to equal minus 5.39 electron volts, Z prime is roughly 1.59. This is not a rigorous derivation. This is just kind of a justification. And where is this coming from? Well, the way to think of, so this is the effective Z value of the nucleus, right? And the way of thinking about this is as follows. This third electron, this third electron sees 3 protons in the nucleus, but it also sees these 2 negatively charged electrons that spend a great deal of time closer to the nucleus than it. And so maybe qualitatively you might think that 3 positive charges, 2 negative charges inside uh, each of the same magnitude uh, has a net result of this electron seeing 1 positive charge inside. But it's further away, right? And so it should be easier uh, for it to escape than it is in the hydrogen case. And that's absolutely what you see, right? It's not this 13.6. But it's not exactly seeing an effective Z of 1. It's actually seeing an effective Z of about 1.59. And again, this isn't a rigorous derivation. This is probably not exactly true. But this is one of those, it's the thought that counts moments. That this electron uh, sees a reduced charge in here because of the inner electrons. And they're not always I the same distance, right? And so we have to be a little careful of just drawing circles the way I drew. Um, but again, it's the thought that counts, and uh, due to the probability of finding it at given locations, the actual effective z value that this electron sees is about 1.59, which is less than the 3 protons that are in here. Um, it's more than the 3 protons minus the 2 electrons worth of charge, right? So it's somewhere in between those values of the net 1 charge you would get if you just took the charge of 3 protons and subtracted the charge of 2 electrons. But it's not as great as the charge of just the 3 protons. So that's what I mean by z prime here. Hopefully that's okay. Let's move on to look at beryllium, z equals 4. This is 1s2, 2s2. Uh, so so in the n equals 2 state, you have L equals 0, M equals 0. This actually has an ionization energy of 9.3 electron volts. From boron to neon, so we're jumping quite a bit here, right? This is from z equals 5 all the way out to z equals 10. So in this case, that outer electrons are n equals 2, L equals 1. Uh, M is either -1, 0, or 1, and M sub s can be plus and minus half, spin up or spin down for each of these -1, 0, and 1 uh, M cases. Yay? So for boron, you have 1s2, 2s2, 2p1. For carbon, you have 1s2, 2s2, 2p2, and then so on and so forth until you get to neon, which is 1s2, 2s2, 2p6. And neon is also inert because it has a very, very high ionization energy, 21.6 electron volts, thereabouts. Um, again, making it hard to do anything with those electrons. So as Z is increasing, so too is the ionization energy. I'll show you a chart of this in a second. For fluorine, um, fluorine is the Z equals 9 case. I guess I could have added that right here. Sorry. It has a hole in its 2p subshell, and this actually allows for ionic bonding. It will happily take on uh, an electron uh, from another element, like perhaps lithium. Um, hooray! Uh, Again, jumping quite a bit, we're going to go from sodium all the way out to argon. This is Z is 11 to Z is 18. So the n equals 3 electrons are very, very far away, and consequently, they are not very tightly bound. 5.14 electron volts, I probably shouldn't have put it that succinctly. That's one case, right? Um, n equals 3 is going to allow L to be 0, 1, or 2. Uh, we have uh, um, oh goodness, this is badly drawn, but um, so sodium to argon, 1s2, 2s2, 2p6, 3s1, 2, 4, 10, 11 electrons here. Argon 2, 4, 10, 12, 18. So from Z is 11 to Z is 18. Argon 1s2, 2s2, 2p6, 3s2, 3p6. When we go to Z is 19 and Z is 20, something interesting happens. Um, what we find is that uh, the the 4s energy is actually less than the 3d energy. And so for z is 19 and z is 20, you actually wind up filling the electrons into the lower energy state first. And so the electrons for z is 19 and z is 20 actually go into 4s before they go into 3d. And so if we look at potassium or calcium, the 19th electron actually goes into 4s1 for potassium, and the 20th electron goes into, the 19th and 20th electrons for calcium go into 4s1 and 4s2. Um, so, so you wind up with this 4s2 state um, before you actually get to 3D. So potassium and calcium look like 1s2, 2s2, 2p6, 3s2, 3p6, potassium then 4s1, and calcium 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2, omitting the 3d for potassium and calcium. From Z is 21 all the way out to Z is 30, we call these transition elements. Um, they behave similarly because their chemical properties are due to 4s, and they're really only differing in their 3D. So the 21st is scandium, and oh goodness, this is going to tax my voice. It looks like 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2 and 3d1, all the way out to zinc, which looks like 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, right? We filled up the 4s's, and then 3d10, right? And so basically, from scandium to zinc, you're really just increasing the number of electrons in this 3D shell every time. And we call them transition. They behave, they have similar chemical properties because their chemical properties are owed to this 4s subshell, and they're really only differing in their 3D filling. And so if I promised you I'd show you kind of this ionization energy as a function of Z. This is hand-drawn sketch. You can see versions of this online that are probably more accurate. But the trend is correct here. So so the ionization energy, remember, for helium was very, very big, which made helium inert. Lithium was small, which made it very, very reactive. Neon, very, very big. Argon, very, very big. Krypton, very, very big. Xenon, very, very big. Your noble gases, right? That's where this is coming from. I suppose if I had been a little more uh, uh, industrious, I could have plotted our ionization energies as a function of Z, right? So let me just show you this, right? Ionization energy is a function of Z, and replicated at least this all the way out to argon, right? So I could have at least given you this in good relief. Let me give proper attribution. I copied this from Gasiorowicz, which is an upper division quantum textbook. This is from page 227. Um, for those of you who go uh, into the physics major or maybe even a chemistry major, this is a common book along with Griffith's. um, that so the Gasiorowitz, Griffiths, J.J. Sakurai. I would be remiss if I didn't um, note that textbook. Um, all common books for an introductory uh, junior level quantum mechanics course. So maybe the next quantum course you took could be out of a book like Gasiorowitz or Griffiths or Sakurai. Um, but and I have all three on my shelf if you ever want to take a look at them. I just stop by my office. But I this is one of the figures that I took from Gus Horowitz. So uh, all right, so I wanted to briefly touch on fundamental forces, strong force, the weak force, uh, E and M, the electromagnetic force, and gravity. Um, so it's this weak force uh, which tends uh, to be associated with some of the stuff that we're going to look at, but in this um, we're going to look at a few different decay modes. The first we'll look at is beta decay. Um, so this is where a neutron can decay into a proton plus an electron plus uh, an antineutrino, specifically the anti-electron neutrino. A proton can decay into a neutron plus an antimatter electron, which we'll call the positron. That's this E plus. And notice that the electron has a charge of -1. The positron has the same mass, but has a charge of +1. So the proton can decay into a neutron plus a positron, antimatter electron, plus an electron neutrino. So this symbol nu, uh, Greek letter nu, is the symbol I will use for a neutrino. And putting the bar on top of it tells me that I'm talking about the anti-neutrino. Yay? For radioactive carbon dating, this is something that matters greatly. If you have carbon 14, carbon 14 can turn into nitrogen uh, 14 by decaying one of its neutrons into a proton, right? This number up here, the top number, is the number of protons plus the number of neutrons. And so here you had 6 protons and 8 neutrons, still carbon. Anything that has 6 protons is carbon, right? So 6 protons, 8 neutrons, carbon 14. You're just going to decay one of the neutrons into a proton, so you still have the same number of protons, sorry, still same number of protons plus neutrons, right? So here you had 6 protons and 8 neutrons for a total of 14. Here we have 7 protons and 7 neutrons for a total of 14. But because we now have 7 protons, it's no longer carbon, right? Carbon has 6 protons. So 7 protons makes this nitrogen, and we had to have gone through this decay process, converting one of our neutrons into a proton, and so we're going to get an electron plus uh, an antineutrino. Um, if you have a large number of carbon 14s, then half of them should have gone through this decay in about 5,700 years. Now, um, why is this useful? Well, I happen to love Milky Way candy bars, right? And uh, they are chock full of sugar, and consequently also have a fair bit of carbon. While you're alive, you tend to take in carbon from the environment through one means or another, um, and the amount of the relative ratio of carbon 14 to carbon 12, it's not common, but carbon 14 to carbon 12 in numbers, there's about 1.3 times 10 to the minus 12. That may not seem like a lot, but remember uh, when we were talking about moles earlier in the semester, that a mole is about 6.023 times 10 to the 23, right? Um, and um, so if you have a gram of carbon in your body, uh, even with this half-life, the time it takes for half of a sample to decay, and even with this uh, scant amount of carbon 14 in the carbon in your body, this is still going to correspond to about 15 decays per minute per gram of carbon in a living organism. Um, now, uh, if uh, if today was the last Milky Way candy bar I ever ate, right? Um, if I were to shed this mortal coil, um, then then I'd stop taking in new carbon, and the carbon that's currently in my body would just decay. And um, and if we look at the ratio of carbon 14 to carbon 12 in my body, well, while I'm alive, I keep replacing it, right? But once I die, I'm going to stop replacing the carbon, and it's going to start decaying. And so we can uh, uh, wait one half life, and the ratio of carbon 14 to carbon 12 should be half as much as it was before. And after two half lives, after uh, what is that, 11,400 some odd years, um, the ratio should be 1/4 as much, right? This isn't a good uh, way of gauging if something died yesterday, but if something uh, is from a prior living organism from thousands of years ago, then we can use the relative abundance of carbon 14 to carbon 12 as kind of a means of gauging how long ago that thing stopped taking in new carbon. Now, um, buried in this assumption is that the relative abundance of carbon 14 to carbon 12 is the same in the past as it is now. Um, but that using other uh, uh, dating techniques, we've actually been able to pin this down, and it is actually a very reliable means of uh, gauging things that are uh, on the order of thousands, tens of thousands of years old. Um, it's not a good way of gauging how long something died, how long ago something died. If it's, if you're talking about minutes, days, uh, even a handful of years, right? Countable number of years. That's uh, uh, not what radioactive carbon dating is meant to work on. We have other ways of gauging that sort of thing. Um, And it's also not going to work for, something that is uh, hundreds of half-lives, right? Because at some point this ratio just gets so small that it's also hard to gauge differences. So um, I'll leave that be. I also wanted to talk about gamma decay. So gamma decay, if you excite the nucleus, and here's kind of my badly drawn nucleus, you could imagine that the protons and neutrons in the nucleus have their own energy levels. They're like particles in a box. And it's not an infinite box, it's a finite box. And the other side of the wall is actually sloped down like 1 over r squared because of the electric uh, uh, potential, but electric field. So this goes as 1 over r for potential, right? Um, but if you promote a proton or a neutron to a higher energy level and then you allow it to fall back down, it's going to emit a gamma particle, which is a photon. So in this case, the way I've denoted that it was in an excited state is I gave it an asterisk. Notice that that didn't change the number of protons or the number of protons plus neutrons. Um, it it just released a photon. There's also alpha decay. Alpha decay is emitting a helium nucleus. I apologize, helium nucleus. So in that case, your parent uh, nucleus has n protons, and A is equal to the number of protons plus the number of neutrons. It's going to decay such that you have uh, some uh, some new atom that has n minus 2 protons and A minus 4 protons plus neutrons, right? Because you gave 2 protons to this uh, ejected alpha particle and also 2 neutrons. Um, so in this case, you have uh, A minus 4 and N minus 2, right? So that you have this conservation going on over here, right? We could look at this uh, for uh, uh, thorium-232. Um, it decays by alpha to radon-228. And again, you also get this helium nucleus ejected. You have to I follow our conservation laws. Um, let's follow this still further. So from thorium-232, we wound up at radium-228. This can beta decay, and it will uh, sorry, I've been talking for a little bit, and I'm not sure where uh, somehow the the audio paused. I'm not sure where it left off, but uh, thorium-232 alpha decays to radium-228, can beta decay twice to thorium-228, can alpha decay once, twice, 3, 4 times to get us to lead-212, um, uh, which can beta decay to get us to bismuth-212. Bismuth-212 um, can decay to Tl208 by alpha, or it can decay by beta to polonium-212. Um, the polonium-212 can alpha decay to lead-208. The Tl208 can beta decay to lead-208. And so we wind up getting to a stable point here. That is all I wanted to say for today. I'm hoping that when I go back and check this, it hasn't been paused for a very, very long period of time. Um, this lecture was already long enough, I guess. As always, you guys are awesome. Have wonderful days. Thank you for stopping by. Don't be strangers. Enjoy your day, but not so much that I don't see you tomorrow. Actually, when